All right, section 14.4. Today we're going to take a look at graphs that are specifically called trees and minimum spanning trees. So definition first. We saw a definition for a connected graph before. This is an alternative definition that's equivalent. It's a graph in which there is at least one path between each pair of vertices. And a tree is a connected graph that contains no circuits. No circuits. Okay, so do you remember what a circuit is? So a circuit is sort of a continuous place where you start in one point, you go around something, and you come back to the same location. So the idea is if I have no circuits, I can't ever get back to the point where I started. And it has to work for every point. There has to be no circuits for it to be a tree. And if you sort of picture a tree, like God's creation tree outside, that makes sense. Right? There's no continuous growing back into itself kind of thing. It doesn't work like that. So the definition works pretty well for what we envision a real tree to be too. Okay, so we've got a couple of examples, and we're going to decide, are these trees? All right, number one, is it a tree? Got some yeses and some nos. And the answer is no. Why is it not a tree? Yeah, it has. Let me see if I've got my images. I don't. All right, let me put these images in the bottom so I can mess with them. Okay, so in this graph, there is a circle, not a circle, a circuit in the middle. It doesn't really matter that it's in the middle, but that's where this one happens to be located. I can start at any one of these three corners, right? That's the corners of this triangle, and I can go around and I can get back to it. So I have a circuit, and since I have a circuit, this is not a tree. How about number two?
Yes.
Do you all agree? Yes. Yeah. This one doesn't have anything like that. This one is a tree. Let me say not a tree up here. Okay, the first one's not a tree because it's got a circuit. The second one is a tree because it doesn't. So if we have a tree, we have something called the unique path property of trees. So in a tree, there is exactly one path from each vertex to any other vertex. Now, you'll remember we've written down like A to B, B to D, D to A, I mean, all these kind of things before, right? These walks, these paths, these circuits, so forth. This is telling you there's fewer ways to do that. In fact, there's exactly one. If you have a starting point and you have an ending point, there is exactly only one way to get there. And a spanning tree is a subgraph, so it just means it's a smaller graph that's inside of the graph we already have, a subgraph that includes every vertex of the original graph and is a tree. So go back to problem number one, the one that wasn't a tree. And what we're going to do is we're going to create a spanning tree for that graph. So we all agreed it was not a tree. There's a circuit in the middle of it, right? But if we were to take this same, actually let me do it from this one down here without the yellow. If we were to take the same ordered point, the same vertices, and we were to take away a branch, or maybe we have to take away take away an edge, or take away two edges, something like that, then we could create a spanning tree. For example, if I remove this edge right here, I now have a tree, correct? It's not unique. I could have removed this edge and created a tree, or I could have removed this edge and created a tree. Any of them would be okay. And the graph that comes about by removing that one edge, in this example, would be called a spanning tree. Okay? So you can take a graph that does not have this property and create a subgraph. Just means it's the same items, but a little bit less. We've taken something away, and it will be a tree. So we're going to do that for this example. We're going to find 3 spanning trees for the graph. There's lots of spanning trees here, by the way. Okay, so if you remember, the condition was that it has to have all of the vertices. So the first thing we're going to do is we're going to draw those vertices that it already had. So we're going to have these same 5 vertices. Feel free to label them, and then I'll copy it so that I can paste it for the other options we do. B, F, C, D, and E. So I got to have all my vertices, and I have to have a way to get from one point to every other point. Now, maybe the simplest option, I'll do it on the top right, is to simply let our edges go around in sort of a circular fashion. A to B, B to C, C to D, D to E, E to F, and we stop. There is a way to get to every single point from every other point, correct? This is a tree. There's no cycles. I've got all the vertices that we had from the original one. I've created in this one a spanning tree. But like I said, there's nothing unique about it. I could have done this in a different order. Remember, it doesn't matter if they cross over themselves, right? Think about like the highways, right, that are on top of one another. Just because they're crossing doesn't really mean there's a point there where they're crossing at. Think of it as a 3D kind of picture. This would do the same thing. Now, they started into different points. That's fine. They didn't give me a condition on that. They could have. They could have told me I really want it to start at A and I really want it to end at E. We could create that. So let's do one more. Somebody give me a point you'd like to start at.
C.
C. Where do you want to go next? A. So C to A. Somebody tell me where you want to. That wasn't very good. Let's try again. Where do you want to go after A?
E.
A to B. Oh, what did you say?
I said E.
E. Sorry. E. We'll go to E. What's next after E?
B.
B. Thank you. And then
F.
F. And then our last point to get to is D. It looks funny, right? It looks like it crosses itself a whole bunch of times, but remember, if you do not see a vertice at the crossing point, there's not one. And think of it like a layered approach, like the highways. Okay, so it's not that there's infinitely many, but there's a lot. Agreed? In fact, if we were to count how many there are, will we do that later? I don't think we do. If we were to count how many there are on highways to do this, do you know what the number would be? It would be a factorial. Yes, it would. I have to pick where I start. In this graph, there's 6 points. So there'd actually be 6 factorial different ways of drawing a spanning tree for this graph. There's a lot of them. Yeah. So, fun fact. You get that one for bonus today. All right. A minimum spanning tree then. A minimum spanning tree is a spanning tree that has a minimum total weight. So you might remember we did some examples of weighted graphs last time. Weighted graphs where they put the numbers along the edges. We talked about it that it could be time, right? Those weights could be time. Those weights could be cost, right? Think about like your tolls, right? Those weights could be distances that you're traveling. And oftentimes when you're looking at this, you're trying to minimize something, right? The minimum cost to get there, the minimum time it takes to get there. the minimum distance your car has to drive to get there, those kinds of things. So we're looking for this one to be the same kind of an idea. We want it to be a minimum on a weighted graph, and we want it to be a tree. So Kruskal's algorithm is a method for finding a minimum spanning tree for any connected weighted graph. So the way that we do this is we don't choose vertices to start at, we actually choose an edge to start at. So the first thing we do is we choose any edge with minimum weight. And the reason it says any edge is because it could have multiple edges that are multiple minimum weights, right? They could all have 5. Several of them have a 5 as their minimum weight. After you choose that first edge with minimum weight, you choose the next edge with minimum weight from the edges not yet chosen. You continue to choose edges of minimum weight from those not chosen without creating a circuit, and you repeat this until we connect all the vertices. So notice when we were doing brute force algorithm and we were doing the nearest neighbor algorithm, we had to go in order. Once we picked an edge, we had to connect it to another edge we already had. Do you remember that? That's not happening here. We're not worrying about connecting them as we go. We just have to make sure that when we're done, it's all connected and doesn't have any circuits in it. So thinking about the 3 algorithms, this is number 3. The brute force algorithm was kind of awful. The reason it was awful is because it's a lot of work. It's very time consuming. But it was guaranteed to give us the best answer. So it did have a payoff at the end. If it was worth it to have that payoff, you did get it. The nearest neighbor algorithm was not guaranteed to give us the best option, but it was mighty efficient. Right? It didn't take very long. It got us a pretty good estimate. It's what your phone does when it tries to get you from one place to the next. This one's kind of the best of both worlds. It's very efficient, it's very quick, and it's guaranteed to get you what you want. Okay? So it's got good features to it. Is everybody done writing all the details? Wonderful. This is a terrible graph, don't you think? It's terrible if it's drawn on your paper. If you do not have it drawn on your paper right now, I don't know that I would draw it. It's a really terrible looking graph. So here's how we start. We start when we're working for Kruskal's algorithm with putting all of our vertices down, just like we did the spanning tree stuff before. We need all the vertices there. So we're just going to do our vertices there. I need to make this a little bit smaller so that I have more space to work. So I'm going to shift it over here. Wow, that's not what I meant to do. That was. So we have A, F, E, and then B, C, D. I think that's all my points. Okay, so far so good? Okay, you have to look at the whole graph. You have to, be careful a little bit, right? But which one is the absolute smallest weight you see? 10. Does everybody find the 10? 10 is the smallest one. So we're going to draw that one in, and we're going to put the number 10 with it. It's FC. It's a 10. That is the smallest one there. Okay, what is our next smallest? Yeah, F to D, which is 11. Okay, so we're going to do F to D 11 out here. Okay, so the first two you're guaranteed to get to draw. The only thing that we could not draw next, for sure, would be CD. Even if it's the smallest, we can't draw CD. Does everybody understand why? It creates a circuit. So as you're thinking through this, we do have some restrictions. We can't just look for the smallest one, draw it. We do have to be a little bit careful. What is the next smallest? It's actually not CD, but what is the next smallest? AC. So AC is 12, so we are allowed to draw that one. And if we had had two 12s, we would just pick one and we'd go from there, right? We draw it and go with it. All right, so after the 12, what's our next smallest? What is it? BF. BF is 15. There's one smaller than that one. BD is 14. Yeah, so BD would be next. That's my 14. I still haven't created any circuits, right? So we're doing good. In fact, I've got an edge connecting almost everything at this point, except for what point's not connected to anything? E. So there's two options. Well, there's not two options. There's more than two options. But I have to get to E from one of the points. So whatever I do next has to be a point that's emanating from, an edge that's emanating from E. So I'm going to have to do either the 30, the 31, or the 27, because it has to connect to E. It's the only thing not connected at this point. And which one of those is the smallest? 27. So does everybody understand why I started looking at the E point instead of looking for the next smallest? Because everything else actually would create a circuit for us. If we had just looked for the next smallest after 14, it would have been 15. Agreed? 15 would have been BF, but if I put B to F, in fact, let me take this off. Do you see the circuit? I'll do it just so you can see. You'd have a big old heart on the outside, right? So at some point, you're going to get to the point where you just need one more edge to draw to get the last edge in there to connect the last point. And you can actually focus on the vertice that gets you that edge instead of focusing on which one's the smallest. That was 27, right? All right, and then it asks us to find the total weight of this minimum spanning tree, which means we're adding all these together. So I have 10 and 12, 14, or 11 and 14, and 27. Should be 5 of them. What is the total weight? 74. It's not too bad, right? It's not too bad. It's efficient. It's not necessarily unique. It could have had the feature that there's another option that would have been just as good if we'd had multiple branches that matched up, right? At some point when we did the 12, I said, hey, if there'd been multiple 12s, we just would have picked one, right? So if that happens, you might have an equivalent, alternate spanning tree that would still be the same minimum weight. So there could be still more than one option, but they will both be the minimum weight. Okay, last thing in this lesson, number of vertices and edges in a tree. If a graph is a tree, then the number of edges in the graph is 1 less than, that's terrible grammar, we're changing it right now. It's 1 fewer than, I know, you guys are like, I don't get it. This is a grammar that faux pas that bugs me a lot, so I'm going to fix it on my own work at least. 1 fewer than the number of vertices, i.e., a tree with n vertices would have n minus 1 edges. Look back at the tree we just created. How many vertices did we have? 6. How many edges did we draw? 5. And if I'd added one more, I would have created a circuit. So it's always 1 fewer than the number of vertices. Okay, last 2 examples. Using that idea, how many edges would there be for a tree with 34 vertices? 33 edges. And how many vertices would there be for a tree with 40 edges? 41. Okay, so these two are simple. They just go back and forth. There is a condition here you need to be aware of. This is only true if it's a tree. And just any general graph, this is not true at all. It's because it's a tree.